All right, so here we go. Let's do this off on the side here. So if I do prime factorization of 30, if you remember, it's like two numbers that multiply to get 30. Well, let's start off, like I think about 3 and 10. And I think of other factors besides 1 in that number. So this actually is done. The 3 is finished. Numbers that multiply to get 10 that aren't going to be 1, that's going to be 2 and 5. This is done. That's 2 and 1 are the only factors there. And 5 and 1, those are the factors there. So what if we test that? What if we do a 5 by 3 by 2 shaped rectangular prism and test that for its surface area? All right, so here it is. We have our 5 by 3 by 2, okay? So let's test this one out and see what we got. All right, so I'm gonna try to move this over here so you'll be able to see it. We'll check that over there. So then, if I know I'm gonna have my top and bottom, okay? Top and bottom, by looking at it here, it's gonna be, so it's gonna be 15 top and bottom there. So let's put that in here. So 15 plus 15. Then my front, that is gonna be 10. So front and back is 10. So put that down. So plus 10 plus 10. And let's see the sides. The sides are going to end up being, that's 6. So 6 and 6. Let's see here. So plus 6 and plus 6. All right, let me move this out of the way. All right, so 15 and 15 is going to be 30, 40, 50, 56, 62. 62 for that surface area. All right, so let's see here, guys. I'm gonna bring it over and take a look. Look at that. Blocks, it's 2 by 3 by 5, the surface area 62, the least possible volume for 30. Hey, that worked. So we figured out a bit of a strategy that when we're looking at the numbers that we're working with, we know the volume. If we do the prime factorization of that number, we'll get the length times width times height dimensions that will be the smallest surface area. That's pretty cool. So we're gonna keep that in mind. We're gonna push on into part B and see what we can discover there. All right. Part B, suppose you need to design a box to hold a liquid such as juice or milk, or a material such as rice, cake mix, or pasta. Because the contents of the box are not identical unit cubes, it is possible to consider dimensions other than whole numbers. So for each given volume, find the dimensions of the box that uses the least packing material. Okay, so again, that's the least surface area. All right, let's take a look. All right, so these numbers, well, this first one, 1,000 cubic centimeters is really, really big. Now remember, we figured out that trick for prime factorization, but we also need to know that this is going to be a rectangular prism, so we need just 3 numbers. So I don't know that prime factorization of 1,000 is going to give us just 3 numbers, but let's still do that anyway, see what we can find out. Okay. All right, so here we go, 1,000. So if I think about this, man, yeah, actually it's going to be a 10 times 100, right? Because you'd add up all the zeros. So the 10 is going to be a 2 and a 5, and those are done. Then if I have this, I'm going to have here a 10 and a 10 again. And this is going to be a 2 and a 5. And this is going to be a 2 and a 5. So when I pull that out, it's going to end up being 1, 2, 3, 2. So 2 to the third times 5 to the third. Now, interestingly, look at that. There are 3 groups of those. And it makes me wonder if we take a step back, notice how we have here, we need 3 numbers. What if I looked at this? These 3 tens, you know? Now, I can't make that with 1,000 cubic centimeters. That would be really, really crazy, but hopefully we can envision it to find the surface area. So this is gonna be a 10 by 10 by 10. So this is really tricky to picture, but let's just think about that for a second. So we're trying to find the surface area, the least possible, but we know that this is gonna be that prime factorization, so we don't need to make it, but I think that's gonna be the process. It would actually end up being, wait, we don't even need to know what it is. Do we just need to know the dimensions? Yeah, it's just gonna be the dimensions. So I think it's gonna end up being 10 by 10 by 10, because we found out that when we had the cubes here, that was the smallest. So we know that's going to end up being the smallest there, 10 by 10 by 10. All right, so from what we saw in the A1 and 2 with the 8 and the 27 and getting that perfect 2 by 2 by 2 or 3 by 3 by 3, and now adding that to this one with the 1000, the 10 by 10 by 10, the closest to a cube we can get with perfect sides is going to be what we're looking for here. Now, I don't know if we can get that specifically with these other ones, but we'll have to take a look. Okay, on to 30 cubic centimeters. Let's do that same, let's try that trick out. Let's try the 30 here in this case. So if I do that, I'm gonna have here, it's gonna be a 3 and a 10. And that's gonna be a little bit, that's done. And then I'm gonna have it that 2 and a 5. And we actually did that one. We did number 4 already. But having numbers closest to that makes me think, this number is really close to 9. And when we did that, it actually, we did 3 by 3 by 3 here earlier. We were really close. We were at 27. So I wonder if it's a little bit closer, a little bit more than 3. Not exactly 3, but a little bit more than 3. So this is tricky to get it exact here in this case. So 7th grade, we're kind of dancing right on top of a concept that's going to be more of an 8th grade concept, where we're looking at something called a cube root. You guys have probably heard about square roots, where if I do the square root of 25, well, it's going to be 5 times 5, or the square root of 49 is going to be 7 times 7. What we're talking about here is a cube root. That means a number times itself 3 times that gets us really close to that number. And we have that with the 8, 2 times 2 times 2. It turns out the cube root of 8 is 2, or 27, 3 times 3 times 3. The cube root of 27 is 3, and we just had it with the cube root of 1000 is 10. So we can't get an exact number, but we're trying to get as close as we can. And sometimes this ends up being something we play around with a calculator. But under these certain circumstances, we'll do that. All right. Here we go. All right, for those of you that have an iPhone, you turn your calculator on, click on your calculator and turn it sideways. You get the much bigger calculator options. So let's just show how that works. So for example, right now, if I did this button here, this is x to the 3rd, that means I'm to the 3rd power. So if I did 2 to the 3rd power, see how I get 8. Or if I do 3 to the 3rd power, I get 27. Or there's that 10 to the 3rd power, you get that 1000. Now there's a little key right below that. We'll learn more about this in the future, but this is called the cube root. This is called that little symbol. It's not a division symbol, it's called a radicand. So watch this, if I push this button, see how it takes me back to 10. It's a cube root of that. If I do 27, and I hit that button, there's my 3 again. If I do 8, and I hit that button again, there's the 2. So let's actually try this with 30 and see what happens. Whoa, it's a really, really crazy big number. And it's wild. We'll talk more about this. It's called an irrational number. It's not a nice, neat number, but let's just kind of work with it in terms. Let's just say it's going to end up being 3.11 times 3.11 times 3.11. Okay, so we'll round that to those 2 decimals. All right, last one we have is 500 cubic centimeters. So here it is. So let's just, again, same process, 500. And we'll hit this cube root button right here. And there it is. It ends up being about 7.94. And again, this is an estimate. It's not exactly there, but 7.94 times 7.94 times 7.94. And this is going to be about, same thing as this one, this was going to be about there as well. It's not as precise. All right, 7th grade. Got a little bit of a sneak peek to that calculator work that you're going to be doing as 8th graders. But let's look at the ACE work here. Today's ACE work is specifically going to only be numbers 5 through 7. All right, here it is, 5. Liquids such as juice or milk and solids such as rice or cake mix are often packaged in rectangular boxes. Because the material settles easily into a box of any dimensions, there are many packaging possibilities. So here it is. What are the volume and surface area of a box that has a width of 3.5 centimeters, a length of 10 centimeters, and a height of 15 centimeters? So you can do that. There's your length, width, and height. And then find the surface area. B, what are the dimensions of the box that would hold 250 cubic centimeters of juice and have a minimum surface area? Again, so there's that shortcut trick, possibly looking at getting minimum surface area with that cube root option, okay? Number 6, The box below is a 6 by 1 by 2 arrangement of drink cans. Suppose the dimensions of the box are in centimeters, so 39, 13, and 12.25. What's the surface area of the box? Okay. What's the surface area of a box with the more traditional 4 by 3 by 1 arrangement, which means in centimeters it's going to be 26 by 19.5 by 20 by 12.25. So they want you to find the surface area of both of those guys. And then last one, number 7, the box below is a 4 by 3 by 2 arrangements of drink cans. Suppose the dimensions of the box are in centimeters. There's 26, 19.5, and 24.5. What's the surface area? What is the surface area of a box with more traditional 6, 4, 1 arrangements, which measures in centimeters, 39, 26, and 12.25? All right, guys, so we're really pushing this understanding of surface area. Remember, if you just draw it out, you can see, but you're going to just find the area of those spaces and then add up all of them. And with all of these, because they're rectangular prisms, there's going to be 6 faces or 6 surfaces there to be sure you add. All right? Good job today, guys. We'll see you later. Bye-bye.